Okay, I'm going to go over an Edexcel paper. It's combined science, physics, higher tier, and this is from 2021. It's worth a total of 60 marks. Question 1. Figure 1 shows part of a wave. It's the height up the side and the distance along the bottom. Use data from figure 1 to calculate the wavelength of the wave. So the wavelength would be from any point to the same point on the next wave. But you can see they don't give us that. But what we have got is half a wavelength, so we'll just double that. So from there to there is half of the wavelength, and that is 14. Just be careful. And if we double that, that'll be 28. A little bit of a tricky scale there. Each 2 blocks is going up by 1. Question B1. Figure 2 shows a student sitting on the shore of a lake watching ripples on the surface of the water moving past a toy boat. The student has a stopwatch. Describe how the student could determine the frequency of the ripples on the lake. So the frequency is the number of waves per second. It would be too difficult to count how many waves there are in 1 second. So if we count how many waves there are in 10 seconds, passing a certain point, and then we'll do the frequency is the number of waves divided by the time, which I've said I like to keep it as 10 seconds. Part 2. The speed of a water wave is 1.5 meters per second. Right, so let's have a look at the equation they're giving us. So that's V, velocity. The frequency of the wave is 0.7 hertz. Calculate the wavelength. Use this equation. So we know what numbers we've got. We know what equation to use. Is it in the form we want? No. We need to rearrange it to get wavelength. So if we do a quick magic triangle, F times by lambda goes in the bottom and V goes on the top. Cover what you're looking for, which is the wavelength, and what do we get left with? V divided by F. Pop the numbers in. And that equals 2.14, and that'll be meters. I'll do it to 2 decimal places because one of their numbers was to 2 decimal places. Always do it to the highest number of decimal places would be my advice. Part 3. Water waves are transverse waves. Describe the difference between transverse waves and longitudinal waves. So transverse waves go up and down. So the energy would travel that way, and the vibrations are at 90 degrees. So up and down. Longitudinal waves the energy would travel that way, and the vibrations go forwards and then backwards. So we say that they are parallel. and this here would be the vibrations are up and down or perpendicular. Question 2. This question is about radioactivity. Alpha, beta and gamma are 3 types of radioactive emissions. Which statement describes all of these radioactive emissions? A. Ionizing and emitted by stable nuclei. No. Unstable. Ionizing, yes, and emitted by unstable nuclei. Yeah, it'll be that one. We'll just double check. Neutral and emitted by stable nuclei. No. Alpha is positive. Beta is negative. So that's wrong. Neutral and emitted by unstable nuclei. No. Once again, neutral, incorrect. Part B. Fluorine-19 is a stable isotope of the element fluorine. The element fluorine also has several radioactive isotopes. Describe one similarity and one difference between the numbers of particles in one nucleus of fluorine-19 and one nucleus of a radioactive isotope of fluorine. 2 marks. So an isotope has the same number of protons or same atomic number because the number of protons is the atomic number, and it's got a different number of neutrons or different mass number. Remember, that's the mass number, which is the number of protons added to neutrons. So since the number of neutrons is different, this number is going to be different. And this number here is just the number of protons, the atomic number. If both of them are fluorine, this number has to be the same. Question C. Figure 3 shows a Geiger-Müller tube, GM tube, attached to a counter. The GM tube is used to measure the activity of a source of beta radiation. There is an aluminium sheet between the beta source and the GM tube. The counter is switched on and after 1 minute shows a count of 268. I've saw students have to draw this before sometimes. Make sure the aluminium sheet is in between the source and the tube. The aluminium sheet is taken away. The counter is reset to 0 and then switched on again. A new count is taken for 1 minute. Explain why the new count is greater than 268. Well, if they've got rid of the aluminium sheet, then obviously more beta particles can get into the tube. There is no aluminium sheet to absorb the beta radiation. So more beta particles reach the GM tube. Part 2. The beta source is then also taken away. The counter is reset to 0 and switched on again. A new count is taken for 1 minute. Give a reason why there would now be a reading on the counter. So why is there still a reading? It's because of background radiation. Background radiation is still there. Part 2. State the SI unit for the activity of a radioactive source. Well, that's becquerels, which is BQ for short. Quite a tricky word to spell. I would just put BQ in your exam. Question D. Radium-223 is a radioactive substance. Radium-223 is an alpha emitter. The half-life of radium is 11 days. A radioactive source contains 1.7 times 10 to the 23 nuclei of radium. Calculate the number of radium nuclei remaining in the source after a time of 33 days. Right, so at the start, you've got 1.7 times 10 to the 23 nuclei. Now the half-life means the time it takes to half, and that's 11 days. So 11 days later, you'll have half of that. Now we've got 33 days. So another 11 days, and it'll half again, and then another 11 days. So that'll be 33 days in total. It'll half again. So if we take this number and we half, then a half again, then a half again, that'll give us our answer, which is 2.125 times 10 to the 22. They gave us it to 1 decimal place, so I'll give it back to them with 1 decimal place. 2.1 times 10 to the 22 particles remaining. And that's how I would set it out in the exam. You wouldn't need to do that bit there. To be honest, if you just put the answer, you'll get the full marks. Question 3. A student is investigating the refraction of light. Figure 4 shows part of the apparatus and the angles to be measured. So the light comes in here. We've got the angle of incidence in between the normal and the incident ray. And then we've got the angle of refraction in between the normal and the refracted ray. That's the angle of refraction, just in case they ask you in a different exam. And that is the angle of incidence. They often ask you about that. The student measures angle R for several different values of angle I. Figure 5 shows the student's results. On the graph in figure 5, draw the best fit curve. Okay, so line of best fit's going to go up like that. Looks like it's a bit curvy. I'll keep it going until we get to the end of the graph. Part 2. Use the graph in figure 5 to estimate the value of angle R when angle I is 80. So the examiners like it when you put little dots on, so that's an angle of 80 for I and the corresponding value of R. If that's 40 and that's 45, then that is 42. 42 degrees. Part 3. Describe how angle R changes with angle I for the results shown on the graph. 2 marks. Right, well, as I is getting bigger, R is also getting bigger, and because it's a curve, it's non-linear or not proportional. And you can also see that whatever I is, R is smaller. So if I is 60, then R is 35. So I've said 3 things. We only need to say 2, but I'll write all 3 just in case. It's worth 3 marks next year for you. So R increases as I increases. It's not proportional, or you can say it's non-linear. R is always less than I. Part B. In figure 4, the frequency of the light remains the same in glass as in air. Which row of the table describes what happens to the wave velocity and to the wavelength of the light when the light travels from air to glass? So the equation is V equals F times by lambda. And it says that this stays the same frequency. Now, if we can work out what's happening to the wavelength, we'll know what's happening to the speed. So let me show you what happens to the wavelength. The wavelength is long at first because the wave travels fast. Each one of these lines is what's called a wave front. Now, as it reaches the glass, it slows down. So it bends toward the normal. So that's your answer. The wavelength decreases. Now, if we come back to this equation, if the wavelength decreases, that means that this wave speed will also decrease. So we're looking for wave velocity decreasing and wavelength decreasing. So the answer is A. The frequency always stays the same because that comes from the source. So unless they're going to be changing the bulb, that's why the frequency stays the same. Part C. In figure 6, only refraction of light is shown. Other things happen to the light as it travels from P to Q. The intensity, brightness of the light at Q is less than the intensity of the light at P. So, in other words, it's bright here, that means intense, and it's dim over here. Explain the decrease in intensity as the light travels from P down to Q. You may add to figure 6 to help your answer. Right, so what's going to happen is a little bit of the light is going to get reflected at that top surface. You'd also get a little bit of light getting reflected there. So it's what we call partial reflection, or reflected partially. And also in the glass itself, you're going to get some light getting absorbed because there could be impurities in the glass. So some light is absorbed. So I'll write that down just in case. So some light is reflected at the top surface. And some light is absorbed by the glass. So that's one of those kind of questions where once you've saw it once, it makes sense and you'll remember it for next time. Question D. Which of these sketch graphs represent the speed of light as it travels from P to Q? Right, so they've got P here and they've got Q there, and it's going from air into glass, then back into air. And we need to decide what's happening to the speeds. So if we go back up and have another little look. So if we did this as a graph, that would be P there, going into Q. Now at this point here, it's travelling in air, so it's travelling fast. And then at this point here, it's now travelling in glass. So it's going to travel slower instantly. As soon as it hits that, goes into the glass, wallop, the speed's going to decrease. And then when it gets to this bit here, it's back in the air. The wave's travelling in air now. So it's going to go back to travelling fast. Instantly there, it's fast. How fast? Well, exactly the same as the speed in the air at the start. So it's going to travel fast, and it's instantly slower as it travels through the glass, and then it goes back to being fast again, exactly the same speed as what it was before. So that's what we're looking for on the graph. And you can see that that is graph B. That's the air where it's travelling fast, instantly slower, travelling through the glass at a slower speed, and then instantly faster as it comes out the other side of the glass and goes into the air. Question 4. Which of these graphs represents an object moving with a constant velocity of 2 meters per second? Constant velocity. Right, just be careful. So they've got a displacement graph here, which is basically distance with a direction. So that's distance time, that's velocity time, that's displacement time, and that's velocity time. And remember, velocity is distance over time. Now, if you're travelling at 2 meters per second, that means you do 2 meters of distance every second. So is this travelling 2 meters every second? So there's 1 second. Has it travelled 2 meters? No. So that's wrong. That's velocity and time. So this is showing us the acceleration. If you're travelling at a velocity of 2 meters per second, that would be travelling, well, there's 2 meters per second, and it would just be a constant speed like that. So that's wrong. Distance, time, has it travelled, so there's 1 second, has it travelled 2 meters in 1 second? Yes. And then in the second second it should go to 4, which it has. The third second it would be on 6 meters, correct. So every second this graph is going up by 2 meters. So it's going up 2 meters per second. So that's your velocity there, the answer is C. That's velocity time. So once again, if you were travelling at 2 meters per second, constant speed, it would be like that. So be careful, don't get your velocity time graph mixed up with your displacement or distance time graph. Question B. Figure 7 is a velocity time graph showing a 34-second part of a train's journey. Velocity time. Calculate the acceleration of the train in the 34 seconds, so from the start to the end. Give your answer to an appropriate number of significant figures, so that'll be for your third mark. Right, so acceleration equals the final velocity, take away the initial velocity, divided by time. So the final velocity is going to be at the 34 seconds, and you can see, right, what's that? If that's 25 and that's 30, then that's 26. So the final velocity is 26 meters per second. We need to take away the initial velocity, which was 14 meters per second, and we need to divide that by the time of the journey, which was 34 seconds. And that comes out as 0.3529. And we need to do it to an appropriate number of significant figures. Now, there's no decimal places here, but it is 2 significant figures. The only data they give us is to 2 sig figs. So we'll give it back to them to 2 sig figs. So 0 is not a significant figure. So that is our first significant figure, and that is our second significant figure. So two significant figures will be 0.35. Calculate the distance the train travels in the 34 seconds. Okay, so if this is a velocity time graph, then the distance is the area under the graph. Area under graph equals distance travelled. So area under a velocity time graph. Okay. So what does this look like? We need to work out all of that area. Now let's take the graph and break it up into 2 areas. So we've got this area here, which is a triangle. And the area of a triangle equals a half times by the base times by the height. So that's going to be a half times by the base goes from nothing to 34. So the base is 34, and the height of the triangle starts at 14 and goes up to 26. So 26 take away 14, which is 12. Half times by 34 times by 12, which is 204, and that'll be meters. And then we need to add this green section, which is a rectangle, and the area is base times by height. So the base is 34 and the height goes from nothing up to 14, and that equals 476 meters. Now we just need to add the 2 together. So 204 plus 476, and that is 680 meters. I'm not writing all that again, so I'll just do an arrow pointing up to the top. Question C. Figure 8 shows a rocket soon after it takes off from the ground. The force that the rocket engine produces remains constant during the first few seconds after takeoff. Explain what happens to the acceleration during the first few seconds. Okay, so what equation do you know that links force and acceleration? Well, it's Newton's second law. Force equals mass times by acceleration. Now, if the force remains constant during the first few seconds, right, what do we know about the mass? So as the rocket is going up, it's burning fuel. And as it burns fuel, the mass is going to decrease. So this number here, the mass, is going to decrease. And if this remains constant and this number is getting smaller, that must mean that the acceleration is increasing. So the acceleration increases because the mass decreases because it burns fuel and it's getting lighter. So 1 mark for that, 1 mark for that, 1 mark for that, or definitely 1 mark for that. I've saw that a few times over the years. It's a pretty sneaky one. But again, once you've saw it once and you've had it explained, you'll know what to do. That tells us about the transformational power of purposeful practice. It's essential to do as many past papers as you can. 5A. Figure 9 shows a small steel ball held at a height h above the ground. The ball is released and allowed to fall to the ground. The height h is 1.4 meters. Calculate the time, so that's our target time, for the ball to reach the ground, and use the equation. Right, so it's gave us the equation. You're not supposed to know this equation, you're just supposed to be able to use it. So it tells us that gravity is 10. So we've got height, so let's pop the numbers in. So it's 2 times by the height, which is 1.4 meters, and we need to divide that by gravity, which it told us was 10. So that's 2.8 divided by 10. So that's going to come out as 0.28, but that's not time. If students make a mistake, they think that's the time. That is the time squared. So now to get the time, we need to square root 0.28. And that comes out as 0.529. And I'll just round that up to 0.53. Question B. 2 students use the arrangement shown in figure 9. They use a stopwatch to time the ball falling through the height of 1.4 meters. The students repeat the measurements many times, but their average value for t is different from the calculated value. So from the value that we've just calculated, which was 0.53. Suggest a reason why the student's value for t is different from the calculated value. Right, are you serious? There's no way that a human being would be able to start a stopwatch and stop the stopwatch accurately, measuring a time of 0.53 seconds. The average reaction time of a human is about 1/4 of a second. So when the ball drops, you'll be 1/4 of the second wrong. And as the ball hits the floor, it'll be 1/4 of a second wrong. So you are going to be 0.5 seconds wrong. Incorrect. And you're only trying to measure half a second anyway. So basically you're going to have somewhere in the region of 100% error. So the best thing to do is to get a computer to do the measurements for you. Doesn't matter how many times you measure it, you're always going to be massively wrong. And that's because the student's reaction time is a significant time compared with the time we're trying to record. The student's reaction time is significant compared to the time they are recording. Part 2. Suggest one improvement the students could make to their procedure so that their value for t is closer to the calculated time. Well, if they don't have a computer available, what they want to do is drop it from a bigger height. And that's because a bigger height will create a bigger time. So their reaction time will become less significant. Or if you want the easy answer, just say use light gates and get a computer to measure it for you. get a computer to measure the time. If you've never seen a light gate, it's basically like that, and there's a little beam of light goes across there. The ball would drop and cut the light gate. You need another light gate down the bottom here. So the difference between breaking that light and breaking that light, that would be your time. Question C. Figure 10A shows a box falling towards a hard floor. The box hits the floor and crumples a little before it comes to rest as shown in figure B. The momentum of the box just before it hits the floor is 8.7 kilograms meters per second. The box comes to rest in a time of 0.35 seconds after it first hits the floor. Calculate the magnitude of the force, so that's our target, the force, exerted by the floor on the box. Use an equation selected from the list of equations at the end of this paper. So if we go at the end of the paper, it's this one here. Force is change in momentum divided by time. Change in momentum divided by time. So how much is the momentum changing by? Well, it had 8.7 kilograms meters per second, and then as it hits the floor, it goes to 0 kilograms meters per second. So it's changed by 8.7. So it's changed by 8.7 kilograms meters per second, and it did that change in 0.35 seconds, and that comes out as 24.8571, and we'll round that up to 25. Well, you could say you're being a bit inconsistent there. I could have left it to 2 decimal places. 24.86 would also be good if you prefer that. State the magnitude and direction of the force exerted by the box on the floor. Well, as the box hits the floor, the force is going to be downward, and the force will be 25 newtons. That's Newton's third law. The floor has exerted a force up, equal in size, 25 newtons, but opposite in direction. The box on the floor here. Part D. Figure 11 shows a ball held in a clamp at R above the ground. There's the ball there. The ball is released from the clamp and it falls. S is 3.8 meters below R. S is 3.8 meters below R. At S, the momentum of the ball is 0.4 kilograms meters a second. Calculate the mass of the ball. Acceleration due to gravity is 10. Okay, calculate the mass of the ball, that's our target. So, what do we know? Well, we know the equation for momentum. Momentum is mass times by velocity. So, if we can work out the velocity, we've got the momentum, we can rearrange the equation to get the mass. So we also know that distance is 3.8. Now, there's a little equation that says the velocity squared at the bottom, take away the velocity squared at the top, or final velocity take away initial velocity, is going to be 2 times by acceleration times by x, which is the distance travelled. And acceleration is gravity, because it's gravity that's going to make it fall. So if you've never saw this question before, it's quite tricky. That's why they make it worth 4 marks. Right, so this is what we're trying to work out. So v squared, now it's not moving at first, so we know that u is nothing. So nothing squared is just nothing, so that's going to get rid of that. That's going to be 2 times by acceleration, which is 10, times by x, which is 3.8. So v squared is going to be 76, so therefore v is going to be the square root of 76, which is 8.71779. Right, I'm just going to put that into me memory on the calculator. So now momentum equals mass times by velocity. So if we do a magic triangle, in case you're not very good at rearranging, mass times by velocity will go on the bottom, momentum goes on the top. It's like a wiggly P. Cover up what you're looking for. We're looking for mass, so that's going to be the momentum divided by the velocity. It told us the momentum was 0.4 kilograms meters a second. The velocity we've just worked out was 8.71779. Never round up if you're using it for a further calculation. And that equals 0.04588 kilograms. We'll put that to 2 decimal places because that's what that was. 0.046 kilograms. Now if you convert that into grams by multiplying by 1,000, that's 46 grams. Does that seem about right for the ball? Yes. So we know we've got it right. And they wanted it in kilograms. So pretty tricky for 4 marks. I know that caught a few people out a few years ago. Question 6a. Sometimes food can become contaminated with radioactive substances. Describe the harmful effects of eating food contaminated with radioactive substances. So remember, irradiated means that you've came close to radiation, but if you've been contaminated, it means the radiation is either on you or it's in you, so it's much worse. So if you eat food that's contaminated, that means that the food, the radiation, is inside the body, and that will damage your cells and could cause cancer. So radioactive food is inside your body. This will cause cancer because it will damage your cells. Always say cause cancer, damages cells. Part B. Gamma radiation can be used in food processing to irradiate food. Explain why some food is irradiated with gamma radiation. So remember, gamma has got a very high frequency. So it's got lots of energy. So if there's any bacteria inside the food, the bacteria will absorb the energy and it'll get killed. So it sterilizes the food. So gamma will preserve the food. So it'll sterilize the food by killing the bacteria. So it stops the food going off high energy and high frequency. You'll not get any marks for that, but I'm just telling you. Part C. Gamma radiation is part of the electromagnetic spectrum. When the nucleus of an atom emits a gamma ray, the number of protons in the nucleus and the number of neutrons in the nucleus does not change. State how the nucleus does change when it emits a gamma ray. So remember, gamma has got zero mass and zero charge. So if a nucleus gives out gamma, it's just giving out pure energy. What happens is the nucleus rearranges the particles so it becomes more stable. So the particles in the nucleus rearrange, losing energy and becoming more stable. And finally, the last question, question D. It's a 6 marker. Gamma radiation is produced by radioactive decay. Alpha radiation and beta radiation are also produced by radioactive decay. Compare the process of alpha decay and beta decay. Your answer should include what each radiation is and what effect each decay has on the original nucleus. Right, so if it's worth 6 marks, let's talk about alpha, 3 things, and let's talk about beta. So we'll say what the particles are, or what an alpha is, and what a beta is. So alpha, it's a particle. So remember, alpha, it's 4,2, so it's got a mass of 4 and it's got 2 protons. So it's basically a helium nucleus. Now you probably won't get an extra mark for that though, because both of those things are the same though. It's got a positive charge of +2. Now what happens to the original nucleus if an alpha particle is given out? So just say this is the original nucleus here, just with all these particles, and if alpha is given off, then you're going to have this, which will be -4 of a mass, because it's just got rid of 4 little particles. So original nucleus, mass number decreases by 4. Right, what if a nucleus gives off beta? Well, beta is also a particle. What the barnacles have are spelt there. It's a fast-moving electron, which is basically the beta. It's got a mass of nothing and a charge of -1. So the original nucleus mass doesn't change if beta is given out. Original nucleus mass number doesn't change. And this is probably a question in itself. Where does the beta come from? Basically a neutron, which has got a mass of 1 and a charge of nothing, splits into a beta particle, which has got a mass of nothing and a charge of -1, plus you get, right, you have to have conservation of mass, so if that's 1 and that's nothing, we need it to equal 1, so that needs to be 1. And what have you got to add? A -1 in order to make nothing. You've got to add 1. So what's got a mass of 1 and a charge of 1? That's a proton. So basically the proton number of the original nucleus is going to increase. So the atomic number goes up by 1. So you decide what 6 things you can remember the best and understand, and then you'll be able to get your 6 marks from that. Right, well, I hope that has helped you. The more of these past papers you do, the better you'll get. Simple as that. The results that my students get is great, and that's because we try to go over as many past papers as we can. Right, good luck in your exams. Work hard and be nice. Bye for now. Want to see more videos like this? Subscribe to my channel, GCSE Physics Explained.